All right, so welcome back to the Civil FE exam review. Today in this video, we're going to be covering the last section of mechanics of materials, and that is the elastic and plastic deformation section. And this will wrap things up. Got a bit technical in the last video, dealing with Moore's circle, but hopefully with this video, it'll be very straightforward. So let's go ahead and dive into these practice problems. All right. So number one says a steel rod of length 1 meter and diameter of 10 millimeters is subjected to a tensile force of 20 kilonewtons. The modulus of elasticity of steel is 200 gigapascals. What is the elastic deformation in the rod? Okay, so what information are we given? We're given the length of the rod, given the diameter of the rod, DIA diameter. We're given the tensile force, and we're given the elasticity or modulus of elasticity. Okay, we're asked to find the deformation. All right, so hopefully you've seen maybe this before. Very popular deformation question. So I just did a search for deformation. And it's axial, so it's this is going to be on loading and deformation, but it's specifically this one, the elastic longitudinal deformation, where we are given, let's see if we know the information. So we're given the force, just P, the loading, so force. Okay, we're given the length of the member of this rod, given the area. Are we given the area? Maybe not. We're given the diameter, which if we're given the diameter of the rod, we can get the area that's being pressed on or loaded. And then we are given the modulus of elasticity. So I know which formula we now need. So we're going to just say deformation is equal to PL over AE. Okay. P is equal to 20 kilonewtons. And I like to put everything in newtons and everything in meters. So just keep everything in newtons and meters. Normally you're able to get your units to mesh well. If you're dealing with millimeters and meters and gigapascals and regular pascals, like it's going to be confusing. So get everything in newtons and in meters if possible. Okay, so I got 20 kilonewtons or 20,000. If you don't know what is what, we're going to visit the unit conversion. We can just actually do that now. Unit conversion. So you're going to search in your bar. Move my head down a little bit. I'm in the way. All right. So in your bookmarks, you can search unit conversions, find unit conversions. And we know that kilo is times 10 to the 3. So that's all I did. I said kilonewtons is times 20 times 10 to the 3, or 20,000 newtons. Cool. So L is equal to, what's the length? 1 meter. Very nice. What's the A? A is equal to, okay, so we get a diameter. All right, so here's what's happening. You have a rod, right? Circular rod. And if you notice, that rod has some type of loading coming on it, 20 kilonewtons coming down. But what the area that we're trying to find is this area, right? It's being loaded. Yeah. So they give us the diameter of that circle, right? But we need the area. So how do we take our diameter and get area? Well, we do pi r squared. So area is equal to pi r squared, which is then equal to pi. What is r? R is going to be our diameter divided by 2, which is 5 millimeters, or 0.005 meters. So I just changed it from millimeters to meters. Pi r and then squared. Okay. What is E? E is equal to 200 gigapascals. Let's go back to A though. I didn't finish solving that. So if we finish solving that, that's going to give us 7.85 times 10 to the negative 5 meters squared. All right. Okay, for E, 200 gigapascals. Okay, can we put this in meters and newtons? So I know, so that everything just kind of meshes well. I know that 1 Pascal equals 1 Newton per. You're able to see this. 1 Pascal. You're not. Okay. 1 Pascal is equal to 1 Newton per meter squared. That makes sense. 1 Pascal, 1 Newton per meter squared. So we have 200 gigapascals. Okay, so how do I get this just in regular pascals? Or 200 times 10 to the 9th pascals. And then why did I say 200 times 10 to the 9th? Well, what is a giga? Is a giga to the 9th? We can always check. It's denoted by G, capital G, and it is 10 to the 9th. So that's where I'm getting this stuff from. Everything's typically coming from this handbook. Okay, so I know that 1 Pascal is equal to 1 Newton per meter squared. So I can then 200 times 10 to the 9th newtons per meter squared. All right, so let's plug. We have P, we have L, we have A, and we have E. Everything is in newtons and in meters, so everything should cancel to get us into the units that we potentially could be needing, which is meters. Okay. So let's plug. Equals 20,000 newtons. 1 meter all over. 7.85. And don't be afraid of these units or these numbers. Slowly write them out and get a, don't forget anything. Don't rush through. That's why practice is so important. Okay. So 7.85 times 10 to the negative fifth meters squared. Okay. What is E? Well, E is going to be our 200 times 10 to the ninth Newton over meter squared. All right. So after plugging all that in, I get 0.00127. Great. But what are my units? Well, I see that my newtons cancel, right? So now I'm left with meters, but how many meters? Is it meters squared, meters to the fourth? Well, we have 1 meter on the top. And then our meters on the bottom, those seem to cancel. Right? Meters squared over a meter squared leaves you with nothing. So that's how I get meters. So I get A for my answer. Alrighty. Let's look at number 2. What does the yield point represent in the stress strain curve of a material? Okay, so we're given stress strain curve. We're trying to find the yield point. Is there a formula that we need? Not necessarily. You must know the stress strain curve. I'm going to see if I can pull up something in the handbook. Okay. So the handbook tries to give us, yes, the only image that they give us. Okay. They give us a stress strain curve, and this is not a good one. But basically, you will need to know this. I mean, I went over each portion of the stress strain curve in, I believe it was definitely mechanics of materials, but it was might have been in deformations like part B or C, but basically I broke down what happens along a stress and strain curve. But for this one, right, I'll just go through it here really quickly. So you got your stress, you got your stress, you got your strain, and then as you increase stress and as you increase strain, there's a point at which this thing begins to yield. And when it begins to yield for metal, or if you're like using a paper clip, right? If you try to unwind it at a certain point, if you apply too much stress or strain, then it's going to do something like this, which here signifies that it is rupturing. Here is the yield point, the point of no return. Here it's kind of like the max or the ultimate stress right here. That's the ultimate stress. And so it's asking us for the yield point on a stress strain curve. So definitely need to know this. Watch the previous video that I made on this to ensure that you get this problem right. But the point, so A is the point where the material reaches its maximum stress. No. Nope. The point where the material begins to deform elastically. No. The point of permanent deformation. So yes, that is the point of permanent deformation and plastic yielding. So it's basically the permanent, right? This doesn't, there's no return. Cannot get it back to the original, its original shape. Okay, so that one is correct. And then D, the point where the material fractures. No, that's at the rupture point. So answer is C. So definitely need some prior knowledge to be able to answer that question. All right, let's look at number 3. All right, this one says, determine the plastic deformation of a material with an original length of 5 meters when subjected to a load resulting in strain of 0.1. I mean, 0.1, not meters. Okay, so we're given the original strength, or sorry, not the original strength. My apologies. We're given the original length. And we're also given the strain for this. Right. Okay. What else are we given? I think that's it. So what are we trying to find? So we're trying to find the plastic deformation. Okay. So it's crazy. We're given the original length, and I was just scrolling through. This looks like where I need to be honest. We're given the strain, right? The strain is this E here. So we're given E, the strain, which is 0.01. We're given the original length. Original length is 5 meters. And so the change in length, or the deformation of the material, is going to be what we're trying to get. So we can use that formula and say It's weird. E is equal to the change in length over the original length. Now, E is equal to 0.01. L0 is equal to 5 meters. And then our change in L, our deformation, is equal to question mark. So that's what we're solving for. So change in L is equal to E times L0 equal to 5 meters, or not 5 meters, equal to 0.01, because that is our strain times our L0, which is 5 meters. And so I get for my deformation or change in length equals 0.05 meters. Okay. All right. So that concludes our mechanics of materials review. In the next section, I believe we're going to be looking at materials. Let's see here though. Don't want to steer you wrong. So yes, we did mechanics of materials. Now we're going to be looking at materials such as mix, concrete mix design, asphalt, test methods, all of that good stuff. So you have made it literally to the halfway point. So congrats to you, 7 of 14. So you are halfway, literally, or almost halfway there. So I will see you in the next video.